Okay, so I thought I'd make some new videos going through a couple of these homework problems. I'm going to make modified versions of it in the video, and so you'll still have to think through a few things in the homework. Here is the homework. So I have a double pulley, meaning I have one object attached at this inner radius of 150 millimeters, and then a second object attached at this larger radius of 250 millimeters. Cylinder A and block B are attached to cords that are wrapped around the pulleys as shown. The coefficient of kinetic friction between block B and the surface. So we're going to have some friction work going on as B is pulled up this hill, knowing the system is at rest at the position shown, and there's going to be a force P that is pushing on block A to get this thing to move. We'll have a constant force problem. Determine the velocity of cylinder A as it strikes the ground. So A is going to fall, B is getting pulled up the ramp, and because of these different radiuses, we can relate how fast B is going to how fast A is going, how much C has rotated. So there's going to be some kinematics in this, and this is at its core a energy balance problem. So anytime you're asked for velocity of something and you have things like mgh going to 1/2 mv squared with a little bit of friction through a distance, work, this is a work energy problem. We have forces through distance. There's not force through time. So force through distance, solve it with an energy balance. Okay, so how I am going to modify this thing. What I did is I edited this image, and I'm going to go ahead and connect cylinder A to the inside radius instead of the outside radius, and I'll connect this block B to the outside radius instead of the inside radius. So that's the only change I'm making. I'll keep the radiuses the same. I'll throw a force on here that's similar, so I'm just going to connect these up a little bit differently. Walking through the energy balance problem, and this is going to be something you want to do one piece at a time. So let's start with the starting energy, T1. That is kinetic energy. I'm not sure why they use the symbol T, but T is for energy. So the new piece that we have for chapter 17 that's different than what we did before is we have rotational kinetic energy as well as translational energy. And for this one, we luck out knowing that the system is at rest. So we're starting with a 0 energy at rest. So all of this first term is going to start with 0. I'm going to skip work, and let's first think through where this thing is going to end. So where it starts, where it ends, and what forces created the new velocity, the new rotation rates. So before we can think about, is work positive? Is it slowing it down? Is it speeding it up? Let's think about what the final positions and velocities are here. Okay, so at the end, block A has moved down 1 meter. Block B has moved up. Can you figure out how far block B is moved if you know how far block A is moved? So you can look at this cylinder, and these are attached to one another. So how much has this rotated that resulted in this movement? It's the same rotation for B, so they're related through these two radiuses. Okay, so the final energy, what we have is we have block A is falling. It has some 1/2 mv squared. Block B is being pulled up. It has 1/2 mv squared. And we have C, the pulley is rotating. So it's going to have 1/2 I omega C squared. So we're going to take our system, and anything that is moving in it, just keep adding those together. Any translational motion, any rotational motion, just add it all together. One thing, so we had velocity of A, velocity of B, rotational angular velocity of C. We have all of these different velocities going on. They're all related to one another. So let's go ahead and get rid of some of these unknown variables by putting everything in terms of, let's say, the angular velocity of how fast this guy is spinning. Okay, so the velocity of A is related to the angular velocity of the pulley by VA equals RA. So this would be 150 times omega C. The velocity of B is related to that velocity of the pulley, same thing. So they're both wrapped around the same pulley, so you have just a different radius going on here. So I'm going to go ahead and get rid of all of these different velocities by just substituting in. So for this scenario, VA is omega C times 0.15, and then VB is going to be how fast it's rotating times a larger radius, 0.25. So now I have everything in terms of that angular velocity. I don't have three different unknowns. So use a little bit of kinematics to whittle down the number of unknowns you have in this thing as you walk through it. Work. So now we're going to look at force through a distance, and this could be mgh, gravitational force through height. This could be 1/2 kx squared. This could be frictional force, but any force acting through some distance that is changing the velocity of anything in there, we're going to just add this up, add this up, add this up for every piece that's in here. Okay, so what kind of work is happening from start to finish? Let's start with A. So there are two different things happening with A. We have 5 kilograms. We have the weight of the thing itself, and that mg is moving through a height of 1. So this is a force through a distance, mg times 1. We also have an applied force, and that applied force is also acting through that same distance. So there's two pieces here. And to understand if this is going to be positive work or negative work, ask yourself, does this force make my velocity faster or slower? In this case, it's making my final velocity faster, so it's going to be positive. This is making my energy, my kinetic energy, larger. Okay, so yeah, work is not up or down or left or right. V squared, this is not a vector, it's a scalar property. So we're not worried about what direction it's going in. It's purely the magnitude that you're keeping track of. So for work being positive or negative, it's purely the magnitude, how it changes. So something has to make it go faster. We have zero velocity going to some positive kinetic energy, right? So this is what's making it go faster. For block B. So now and there's actually quite a lot of things going on with block B. So it is sliding up the ramp. We have some kind of a friction force, so we'll have to draw a free body diagram. Here's the mg cosine theta is going to be our normal force. We have a friction force that is a friction coefficient. So we have, here's the kinetic friction between the surface is 0.2 times our normal force, and that's going to be our mg cosine theta. And then the distance that acts over, so however far it pulls up here, can you figure out what that distance is if I know A has fallen 1 meter? So how much is this rotated for A to fall 1 meter, and that means that B has now moved how far? Okay, as well as the friction force happening here, B is also getting pulled uphill. So this is an mgh, only I'm putting this in as a negative because it's being pulled uphill, not falling downhill. So pulling this thing up is slowing it down, and the friction force is also slowing it down. So we have two negative work components that B is adding to it. So for our mgh, the height that this is going to be pulled up the hill, that's going to be the length that scoots up the hill, and it will be opposite this sign. So the sine theta, that's the opposite piece of this. Okay, just a quick note. I skipped C rotating. So this original moment through a theta, so you can say, oh, if I look at the moments on C, I have radius to a tension pulling over here, radius to a tension pulling over here. There's some things that you can do to simplify this system. So I could have carved this up and just looked at starting energy, ending energy for A, in which case I would have to know what the tension of this is. And then I could come over here to B. I could look at the starting and ending energy of B. And again, I would have to know this different tension. This is a different rope on the outside than the inside. And then I could look at just C separately and all of the moments acting on C, that originally it's not rotating, and then a moment is applied, and at the end of it, it is rotating. If I look at each of these separately, I would have to solve for each of these tensions. There would be more unknowns that I have to solve for. If I take all of these equations and I add them together into just one monster equation, so I'm looking at everything, all of the starting kinetic energies, all of the starting works, all of the ending energies, and I just put it all into one giant equation, I'm going to help myself by getting rid of internal forces. So the tension on my pulley is pulling down on my pulley, but the same tension is also pulling up on my block. So when I add together the work done on my pulley to the work done on my block, that would be equal and opposite, and it would cancel out. Same with this. So the tension pulling down on the pulley is also pulling up on the cylinder A. And if I add A to what the pulley is doing, those two guys end up canceling out. So if I start out and I define my system as being anything inside this circle, so kind of draw a circle, make your system borders, you can make life easier for yourself by getting rid of anything internal to that system versus if I'm looking at these things individually. So if I'm just looking at block B, then I'd have to worry about the tension. I'd have to worry about everything happening on block B. So it's just, you can play games with how you define your system boundaries to make life easier on yourself. And yes, there is moment acting through a theta in this equation, but if I add everything together like this, I don't have to worry about it because those tensions become internal forces. And for my system, I'm only worried about external forces, any force that crosses that system boundary. Okay, so taking this thing in, let's figure out how far block B has gone. If I look at how far A has fallen, so it's rotating the pulley to fall, right? So if I look at 1 meter, that is 1 meter of string that has unraveled, which means R theta. That's how many radians that this pulley, so it's actually gone all the way around. It's made one full revolution, a little bit more for this block, for the cylinder to fall. Okay, so then when you see the angle that had to rotate through for A to fall, now we can come over here and say, well, the pulley is attached, so it's the same angle that's also pulling block B up that incline. So if we figure out how much it's rotated through this system, I can plug that in and say, oh, this is how far B has been pulled up the incline. So a little bit more kinematics. Distance is equal to R times theta, just like circumference is equal to 2 pi R. Arc length is equal to R times theta. So use some of these relationships again when we're coming back here and figuring out how far has the friction force acted, what height has that MG been hoisted up to. So use those kinematic relationships. Okay, so here we are over in Mathematica to plug some numbers into this thing. I'm going to start out with my kinematic relationship. So I'm going to remind myself that the velocity of A at the end of this is going to be how fast C is rotating times the radius, and I'm getting everything over here in meters rather than millimeters. Here's the velocity of B. The velocity of B is going to be however fast C is rotating times the radius that B is attached, so that's 250 millimeters. The angle that this rotates through as A falls. So what I'm saying is 1 meter and that's the arc length of string that's wrapped around this edge, is 1 meter is going to be equal to that 0.15 millimeters times whatever angle that this thing rotates through. So if I want to see what angle I've rotated through, I'm going to say 1 divided by 0.15, and then I can apply that angle to see how far B has slid up the hill. So B sliding up the hill is going to be the radius that B is attached up there times the angle that the pulley rotates through. Okay, so I have my distance, I have my angle, I have how velocities are related to my angular velocities. My final kinetic energy. So A is moving, B is moving, C is moving, and then I'm going to go ahead and take those velocities and get them all in terms of the angular velocities of my pulley. So A is related by 0.15, B is related by 0.25, and then for the pulley itself, I have the inertia of the pulley times the angular velocity of the pulley. So plugging in numbers, I have the mass of the pulley, the radius of gyration of the pulley. The radius of gyration is what you use to calculate the moment of inertia. So r squared m, we're using that radius of gyration times the mass of the pulley. I'll make sure G is 9.81 because I have some MGH going on in here. We'll throw a force acting on top of the cylinder A. Here's the mass of A. And here is that angle that we're going to rotate through, knowing that A is falling 1 meter. So I kind of have everything A related right here. For B, I have the mass of B is 15 kilograms. And then here is the distance that B is sliding up this hill. And again, that's going to be R times theta, 0.25 times however far C is rotating around. If I draw a free body diagram of this thing, I can see the normal force for B is going to be cosine of this 30 degrees. I can use that for my friction force, and let's walk through the energy. So I have starting energy of 0. I have an ending energy of A is moving, B is moving, C is rotating. So there's my final energy. And then the work to go from one to the other is MA8. So mass A is falling. That force is acting through a distance. I have my friction force. So friction coefficient times the normal force, which I have defined up here. And then the distance that it's traveled, which is also defined up here. And I also have MGH, where the height that this thing is hoisted up the hill is the sine theta, the opposite side. So we have how far it's scooted up, and then opposite of sine theta. So if I walk through each of these terms and make sure everything is in there right, signs are correct, what I'm solving for, and I've whittled everything down to where everything is dependent on the angular velocity of my pulley. So that is actually the only unknown I have in this whole thing. I could solve this for just the angular. It actually asks for the velocity of A, so I'm going to put one more equation in here so I get the velocity of A out of that too. And I get how fast this thing is rotating. This is going counterclockwise, so we're going to put a positive rotation on here. And A is falling down, but V squared, you're not going to get the direction of this thing out of an energy balance. You only get the direction from the diagrams, looking at the pictures of it. But that's at least the magnitude of what A is doing right before it smacks into the ground. Okay, so a lot of pieces to keep track of in this, but hopefully that makes sense for how to walk through that energy balance, that draw your system boundary, look at anything that's moving starting out, anything that's moving at that last step, and what happens between time 1 and time 2. That's what it all comes down to.